Hello, everyone, and I'm glad that you could join us today for our regular GPSX webinar. So today we're going to be talking about optimizing nitrification and denitrification processes using the GPSX platform. And this is actually the first of, I guess, a sort of a loose two-part series that we're going to do on nutrient removal and how to use tools like sensitivity analysis and numerical optimization to help you be able to sort of optimize and improve and analyze the process that you're putting into GPSX. So my name is Spencer Snowling. I'm Director of Digital Water Solutions here at Hatch, and I'm glad that you can join us for today's webinar. Okay, so the plan for today is that I want to talk a little bit first about how we actually model nitrification and denitrification in GPSX. So I won't dwell on it too much, but I wanted to show you at least a couple of equations so that you have a feeling for how the parameters that are in those equations work, because those are things that you have access to in the software. You can adjust the calibration of the model by changing a half saturation coefficient and so on. So I'd like to be able to show you a little bit about those things first. Then we'll move on to talking about doing sensitivity analysis for process design. So I have a couple of examples cooked up here to show you where we're going to take a look at, in the beginning anyway, one parameter at a time, adjusting that, seeing how that affects the process design, seeing how it affects the nitrification and denitrification of this particular facility that we're going to use as our case study for today. And so we're going to look at the effluent total nitrogen and see, does it go up and down, and how is that affected? So then we're going to move on to a little bit more complex plant, and then we're going to look at using the GPSX optimizer tool, the simplex optimizer, where you give GPSX control of some of the parameters that you're interested in analyzing, and then we run simulations, and it uses a search algorithm to find the details, find the best combination of parameters that gets the job done. So there will be 3 desktop demonstrations all together today. And then, as usual, I'll answer any questions that you might have. So if you've been with us before for a webinar, you probably know that you can use the GoToWebinar dashboard, pop out the questions panel, and then open that up, and you can type your question in there, and I can see that, and I believe others can see it as well. And then I will take time at the end of the webinar to answer at least a few of those. Any other ones that I don't get to, I will follow up with afterwards. Okay, moving on. So simulating the nitrification and denitrification process is really a fundamental part of the ASM type water, wastewater models that exist in our industry. So it's been there right from the very beginning. So modeling nitrification and denitrification was part of ASM1, even though it was a slightly simpler approach back then. So the conversion of ammonia to nitrite and then to nitrate and then subsequently denitrifying into gas is described through a series of several process steps. And we have a whole set of equations that kind of come to life under the appropriate circumstances and do the steps in that process. And you can see details about that through the output menus and see sort of how far along you are in that process. So there are a number of different biomass types in the models that we use here. So I'm going to be talking today about our in-house standard basic Mantis 2 model. That's the one that most people use in GPSX. And you can see the number of different biomass types there. They're involved under different circumstances. And so I'm going to go through and talk a little bit about those as well. So the Mantis 2 model allows you to plot a lot of information about what's going on throughout your BNR process. So you can plot a lot just by looking at the concentrations that are available. You can also go to the output variables menu and then go to internal variables, and you can see basically you could plot the value of each row or each step in that process and use that information to help sort of understand what's going on in your system. Okay, so starting with nitrification, and I'm talking about the Mantis 2 model here. The nitrification process in our model is described as a 2-step process, so ammonia to nitrite and then nitrite to nitrate, and we have 2 different biomass types to be able to do that job. So we have an equation for each set of growth circumstances for each biomass type. And the AOBs and the NOBs are modeled in separate steps. So this is what the growth equation looks like. Now, I've kind of simplified it just a little bit from what we actually use in the software. There's a few more terms on the end for other types of inhibition. But for the most part, this is a traditional first-order growth rate with Monod saturation term type growth equation. So the most key important part of this model is that this is a first order relationship. So mu max is the growth rate for AOBs, and XBAA, that is the amount of biomass that you have in your reactor. So that means the more biomass you have, the more it's going to grow. And so that is one step in this process. We have an entire separate step for doing the decay so that we have that growth and decay methodology that's sort of a fundamental foundation of the ASM type modeling system. So as far as growth goes, when this equation is going to describe how fast the growth is happening. And then there's a separate part of the mass balance equation that takes care of, okay, so for every unit that this goes forward, for every new unit of growing of AOBs, we are going to use up a certain amount of ammonia, and we're going to use up a certain amount of alkalinity and oxygen and so on. We're going to produce a certain amount of nitrite and so on. So I won't go into all the stoichiometric part of the model. I'm really interested in the kinetics that you understand that today. So just to cover what this equation looks like when we're doing nitrification, we have that first order relationship, and then we multiply by each of these other terms here. So this term is the saturation term for ammonia, and that is basically there to turn off this growth when we run out of ammonia. So this half saturation term here, KNH4, this is the one that kind of controls turning off the ammonia. So it'll control how low you can get with growing AOBs. This is the term for oxygen. KOA is the saturation term for oxygen. Again, it's sort of the term that controls the sensitivity of the AOBs to the oxygen in this case. So if you run out of oxygen, maybe you can keep getting some growth all the way down to say, 0.5 or 0.25 or something like that, or even lower. You can adjust that in order to be able to control that. And then these last two terms are actually inhibition terms. You'll notice the K, it's the K value, the saturation term is on the top and the bottom. It's actually an inhibition term in this case. And these are here actually to represent and to turn off the growth of the AOBs under certain inhibitory situations. So this one here is for nitrous acid, and this one is for free ammonia. So in both of these cases, the concentrations of those are being predicted by the model. We have a pH model, so we can tell the difference between the charged and non-charged forms of these components. And then we have these terms here to control, by controlling this K value, the presence of these things would cause the ammonia to be, the AOBs to be inhibited. And so these terms are here, and they're very important for situations where you're often trying to do things like side stream nitritation, where you may have, after your digester, very large concentrations of ammonia. And that might be enough to have that potentially small fraction of that ammonia, which is going to be the inhibitory part. That might be still big enough to actually slow you down. So the AOBs and the NOBs both have this term, and they both do it to different levels. So that's how you can get sort of that NOB suppression as part of that process. Okay, so here's the same equation for NOBs. And so same thing, first order growth rate times that saturation term. Now, of course, this time it's on nitrite. It's not on ammonia, it's on nitrite. It has its own oxygen term, and it again has the two inhibition terms there as well. So again, these are there, and these values of these inhibition constants are different for NOBs than they are for AOBs. And so it allows us to use the same form of the equation, but because each one has its own values, they're going to behave slightly differently from each other. And that's actually true for almost all of these parameters that are here, including the growth rate. The growth rate, by the way, I should mention, is actually corrected for temperature. So we use an Arrhenius relationship here. The number that you're typing into the menu when you see it in GPSX is for 20 degrees Celsius, and then we correct it based on whatever temperature you tell us that you're using. And so we use an Arrhenius equation for that. And some of the other parameters are also the same way as well, like the death constant and so on. So these are all here. And this is kind of like how we describe how things are going forward with our nitrification. Okay, so what I want to do is really quick, just pop over to GPSX, and I'm going to show you the kinetic menu. Now, you may or may not have actually gone digging around in this menu much. It's one of the biggest ones we have in the biological model. So if you go to input parameters and go to the kinetic menu, this is the place that we store all of the parameters and their values of the things that I was just talking about, the saturation coefficients for ammonia and oxygen and all of those sorts of things. And so we organize these by biomass type. So at the top here, you'll see heterotrophic biomass. So if you slide farther down, here's AOBs, ammonia oxidizing biomass, and here's NOBs right below. So these two are the ones that I was just talking about. And some of the parameters that we're using, like this inhibition coefficient for free ammonia, these ones here are the values that you have. So if you'd like to make your simulation a little bit more sensitive or a little bit less sensitive to certain aspects, then you can do that. And so you can make them more or less sensitive to oxygen and other things as well. So that's where you would find that information there. Okay, back to the slides. Okay, so normally, of course, what happens in a plug flow activated sludge system is that you can see the nitrification happening as you go down the length of the reactor. So in a situation like this is a plug flow tank. Despite it being only one object on the drawing board, it's actually 4 reactors in series. And you can see, as a result of running that simulation, I've actually gone in and plotted a bar graph of each of these different species as we look at how this thing does its nitrification. So now it goes downstream as you go from left to right. So the ammonia coming in, this is a plant where the ammonia coming into the facility is at 25 milligrams per liter. That's our default value. So here it's showing it that it's like about, where's my mouse here? About 10 or so, and then down to about 3 or 4, and then fully nitrifying. The ammonia, by the time it leaves the bioreactor, at the end of that plug flow bioreactor, the ammonia has been mostly oxidized away. So here's the nitrite and the nitrate. So it's generating that intermediate step of nitrite, and then the NOBs are also doing their job. They've got lots of air, they've got a growth rate, and it's whatever's being generated is mostly being consumed and then generated over here to nitrate. And so that is accumulating as you go down the length. Now, actually, in a lot of simulations, and even under our regular default conditions, this will pretty much be 0 in the middle. I actually had to back off the SRT and the oxygen a little bit so that it left a little bit of this hanging around so that I could use it for our demonstration today. Okay, so that's nitrification. That's relatively straightforward first order relationship, and you have your growth rates and so on. Now, denitrification fits in when you have your nitrite and nitrate available, and you want to be able to denitrify that by having an anoxic zone and some more biomass, and then they can convert nitrite and nitrate into gas. And these are different biomass type, of course. These are ordinary heterotrophs, and I also put methylotrophs here as well because we do have that in GPSX, a whole separate biomass type that uses only methanol as its substrate. And so these things are then working in concert. And this is, of course, as it is with activated sludge, these are all happening together in the same tank at the same time. So now I'm going to come back and talk about this and show you more details later. They're happening at the same time, but not to the same extent, because generally these are aerobic processes. So it means you need to have lots of oxygen. The equations are set up with those switching functions so that they're only active when there's a lot of air, a lot of oxygen available. And then these ones are anoxic processes, meaning they are only active when there is not a lot of air around. Now you can have, as I will show you a bit later, you can have simultaneous nitrification and denitrification by operating at a real sweet spot there in the middle. And we'll use our sensitivity analysis a bit later on to find out where that is. So, but these processes are all set up in GPSX, in the Mantis 2 model to be able to do denitrification with these 2 different biomass types. There's actually a few others that do it as well, but I'm just going to stick to talking about these 2 today. So again, to talk about the equation, it's basically the same kind of approach again. Again, a first order growth rate equation. So we have our heterotrophic growth rate times the amount of heterotrophs that we have. And then we have a saturation term for the nitrate. We have a saturation term for phosphorus. So these two things have to be present in order for the denitrification to happen. Then we have to have substrate. So, and now I called it sub here, SUB. There's actually many different kinds of substrates available in GPSX in the Mantis 2 model. So we actually have 6 versions of this equation. And it is for each of the different types of substrate under each of the different conditions. And then we have it for nitrate and we have it for nitrite. So there's this big chunk of our matrix that is covering the denitrification process. And this is an inhibition term on oxygen, meaning that we have to have an absence of oxygen for this equation to work. If the oxygen is, say, much higher, if this value of the oxygen, the concentration, is much higher than this value, then this whole bit's going to go to 0 and then multiply the whole thing by 0, and then there will be no denitrification. So you have to get oxygen down to a certain level for it to work. And then this equation, or this last term here, is the anoxic reduction factor. So this is actually related back to this thing. I probably should put it at the other end of the equation here. Basically, this is the rate, the same rate, that's using the same growth rate that you would for aerobic growth of heterotrophs. So that's just doing regular BOD removal. But then we multiply it by this term here, amongst everything else. And this is a number like 0.4 or 0.5 or 0.3, something like that. There's different values for different circumstances. And this is going to basically dial back the growth rate. So it's the same proportional growth rate, but when it's in an anoxic zone, it only goes like 30, 40, or 40% of the speed that it would when you're running it in an aerobic environment. So if you're trying to calibrate your denitrification and you don't want to mess up the rest of your model, you can come and adjust this parameter. And then that will adjust just the denitrification part of it by itself. Okay, so that is what it looks like for heterotrophic organisms. And as I said, we have a big set of values for this for nitrite, nitrate, and then each of the substrate types as well. Now, the exact same equation is used for the methylotrophs. That's for a different biomass type. So, and basically it's exactly the same type of equation. It's just that all of these parameters have their own separate values for methylotrophs. And also, when this is the kinetic rate equation. When we get into the stoichiometric ratios, they're actually a little different too for the the methylotrophs than they are for the regular heterotrophs. So, so nonetheless, there's also the methylotrophic organisms doing the same thing there too. And if we go back to that menu, you can find all the details on that in the same place. In the kinetic menu at the top here, there's the heterotrophic biomass. Here's all the different kinds of parameters that we have, saturation terms for acetate and propionate, and also the regular substrates, oxygen. Here's our reduction factors down here for denitrification as well. So I was saying it was around 0.4. There's a 0.32 and a 0.48, one for nitrate and one for nitrite, and so on. So all of that is there. And then if you slide a little farther down, here's all your details for the methylotrophs. Okay. Move on to the next slide. Okay, so now I want to get to the more interesting part. It's only so interesting looking at equations. Let's actually apply them and get to doing some simulations here. So I'm going to be working today with the MLE process. So most of these examples I'm running are just a simple MLE plant, which has an anoxic zone ahead of an aerobic zone. And so as you probably know, basically what we're doing here is we're having ammonia coming in the front. It passes through into the aerobic zone, in which case it is nitrified. And then this internal recycle takes some of that nitrate back to the anoxic zone, where it's going to use some of the carbon that's coming in through the influent to do denitrification there. And then that's going to pass through. So there are a few things that are process choices that you would be making if you were designing a system like this, or what is the relative size of this tank and how much of that size, what is the anoxic zone fraction of that, and how much should this internal recycle be with respect to the amount of flow coming in, and then the usual activated sludge questions you need to ask, such as what is my RAS flow and how much am I wasting and what SRT and mixed liquor do I want to run. So there's a lot of decision making there, and we could spend probably a whole half day on this rather than a 45-minute webinar here. But nonetheless, we're going to talk about the anoxic fraction, and we're also going to talk about carbon addition a little bit as well. Okay, so this is what it looks like when you do that in GPSX. So these are results that came out from a simulation that is actually one of our sample layouts where we have an anoxic zone. It's actually a separate tank in that particular case. And you can see here on this side, this is showing the ammonia here. It's coming into the anoxic tank, and then it's as we go through the aerobic part, it's being nitrified. And that's producing nitrate. But here, where on this side, where we're showing nitrate, we can see that after it leaves the end of the aerobic zone, as it was accumulating, where we were generating that nitrate, and that gets recycled back to the anoxic zone, this is much lower over here because this is where the denitrification is happening. So that is what we want to be able to simulate and to optimize. So what I'm going to do is I'm going to run a couple of simulations with a plant that looks like this. And if you are new to GPSX, or maybe you don't know about taking advantage of our plug flow tank configuration on our drawing board, I just wanted to highlight that you can set up the MLE process just with these 5 objects. And basically the MLE tank here, this is actually 4 zones. So if I blow that up here, this is actually 4 zones in series, and you can step feed the flow coming in if you like. You also have control over the aeration and all of these zones separately. So you can set up your MLE process here by, first of all, setting that initial very first zone to be anoxic. So the way I've done that in all of my examples is I have DO controllers on, and I have a DO set point of 2 for each of these latter parts over here, and a DO set point of 0 here, which means by default it's just going to turn all of the air off. And then the second thing you can do is put an internal recycle. So on your GPSX drawing board, you won't actually see the internal recycle. It's actually just there inside the object. But I find this way is a little easier to manage, especially if you have a very complex or detailed plant and you got lots of objects and flows moving around on your drawing board. Sort of tidying it all up and moving it inside one object can be very helpful. It is actually also a nice way because inside one of these objects are a number of nice ways to plot bar graphs of the profile of down the length of those tanks in series. So a lot of the outputs that you'll see today are based on being able to do that. So you can, if you like, explicitly put out CSTRs and make some of them anoxic and do that. That also works. It works out to mathematically the exact same equation, except that here it's all just sort of handled a little nicer in terms of the flow of information. Okay, so let's start out by doing our first sensitivity analysis on the anoxic zone fraction. So, all right, whoops, here we go. Okay, so this is our regular GPSX. This is version 8.1 if you haven't had a chance to see it yet. I'm going to go over to where I have a number of things set up here. And in my MLE tank, we can see that we have simulation that I want to run here, and this plant is actually not very big. It's close to our default size. And I've got a few things on control up here so that we can play around them. A little bit of process control here. I'm not going to be dealing with these very much. I've got it all sort of nicely set up to have, 2,000 milligrams per liter mixed liquor. It's got an SRT of about 7 days or so. So it's in the right spot. This is the anoxic zone fraction that I want to play with. So by default, it's 25% of all of the volume. So the first 25% of this plug flow tank is anoxic. And you can even see that here. If I look, I've got that first DO set point set to 0. Okay, so let's run a simulation. Okay, so now I'm going to pop over and we'll take a look at the effluent numbers over here. So we can see the ammonia is 0.1. So that means we're fully nitrifying. And our nitrate is 0.7 roughly. Or sorry, 6.7, and our total nitrogen is like 9.3, 9.4. So that's not too bad. We got it just under 10. Now, if I were to sort of just manually play around with this number, you can investigate and kind of get a feel for how this system responds to the size of the anoxic zone. So if I were to knock this down to say 15%, So there you go. Actually, you know what? I'm just going to type in 15%. And we'll run that to steady state again. So now we can see here that our ammonia is still 0.1, just a shade higher, but it's not bad. Sorry, a shade better. And then we can see here that this is 9.7, so it's up a little bit. You know, not so bad. But the nitrite had actually come down a little bit. All right, so that says that we can get away with shaving off a little bit of that anoxic zone. But what happens if I knock it all the way down to 5? So basically, we don't have very much anoxic zone at all. Well, then we can see here that we went previously from 9.3 to 9.8, and now it's at 12. So that means we've actually gone too far. That's not actually beneficial. We don't have enough anoxic zone in this particular system to be able to do all the denitrification that we want to do. So, and just for experiment's sake, what if I move it all the way up the other end and I make it 75%? So 3/4 of this tank is anoxic and only 1/4 is aerobic. And if I run that, then we'll see completely different circumstances. Our total nitrogen is actually even higher. It's now at 19. What's happening in this case, though, is our nitrate is basically 0 because we're not really nitrifying that much anymore. So our effluent ammonia, where it was supposed to be 0.1, is now 16. So there's really not very much nitrate to actually get rid of, and we got all sorts of anoxic zone to do that, whatever actually does manage to get nitrified. So of course, this is obviously not an optimal thing as well. Okay, so I'm going to reset all this, and then what we're going to do is we're going to use the sensitivity analyzer feature, which is this button right here, to do a sensitivity analysis on this parameter. So first thing I have to do is go in here and switch that from a slider to analyze step. We have two different kinds of analyzers in GPSX. One is a simple stepwise mode where it goes from the lowest value to the highest value and keeps track of and runs a simulation at every step in between. And we also have Monte Carlo, which is a whole other different thing. And we have a really nice webinar on that I did last summer that you can see on our YouTube channel. Okay, so now the next step is I have to turn on the analyzer. So I'm doing that. You'll notice we have different forms of it. I'm just doing steady state analysis. So it's going to step through here about 10 steps along the way. And I'm going to collect all of the results for each of the sensitivity steps for each of the steady state solutions along the way. So you'll notice now down here along the bottom, it's not actually showing, here, let me blow that up for you. It's not actually showing time down here. It's showing the anoxic volume fraction starting at 5% all the way up to 75. So let's run the analyze mode here. So what it does is it does one simulation after another, and it solves it for steady state each time, collects all of the results, and it plots anything that you want versus the independent parameter that you were changing. So right now what we're plotting is effluent numbers versus anoxic fraction. And this is a nice handy tool to be able to see that relationship just in one dimension of how everything changes. Now, this is sort of a more automated way of doing that manual thing we were doing before. So first of all, if we look at ammonia, we can see, well, if we have a very small anoxic zone, we got lots of aerobic zone. Obviously, our effluent ammonia is very low because we're doing lots and pretty much full nitrification. But as we move across and we get over here to like, say, 50 or 60, 70%, it's pretty much, we lose it all. And so suddenly our effluent ammonia goes way up and we're not nitrifying anymore because we don't really have enough aerobic zone anymore. It's interesting to see what nitrate is doing. So here, when it's got full nitrification, but not very much anoxic zone where we're not really doing any denitrification, then there's some sort of better spot in the middle here where we're doing both. And then once we lose nitrification, well, there is no effluent nitrate to actually accumulate. So because we're not actually producing it in any way. So the best one that kind of, to me, tells the story is this one, which is the total nitrogen number. As we were showing before, if you go too much one way, then you're going to have all nitrification and no denitrification. And if you go the other way, then you're going to have no nitrification and whatever amount of nitrate that you generate is going to be denitrified. So there's that sweet spot in the middle somewhere. And so this relationship tells us the lowest point of our total nitrogen is over here around 45 to 50%, somewhere in this neighborhood here. So that's how you use a sort of simple one-dimensional sensitivity analysis. You pick the parameter that you're interested in, you plot the things that you want to see, and then you let it do its job, and it runs a number of simulations. And you can see here, well, if I wanted to optimize for the lowest total nitrogen, I can figure out what volume fraction that I should be using. Now, I should say, of course, this is under the given conditions that we have. Like, so we were changing the volume fraction, but it wasn't, everything else was being stayed the same. So if your influent was different, if you're at a different temperature or a different SRT, this number might move up or down or sideways. You know, like it's a relationship based on all of the settings of the model. You're just changing one of them. Okay, so I like doing sensitivity analysis a lot. It's really good. We do it a lot during our times when we are developing up models of various technology. We know that there should be a certain kind of relationship, and we want to be able to see that the model is able to produce that. Okay, so let's take a look at the other issue that often crops up when talking about denitrification, which is a deficiency of enough carbon to grow your heterotrophs when you're in the anoxic zone. So if you've already passed through some aerobic zones, you will have, of course, removed probably all of the soluble substrate that's available that's there. So when you get to an anoxic zone, you may find out that you don't have enough. So you may have to add some. Now, of course, that's the benefit of the MLE system, is that it recycles it back upstream to the point where there's hopefully at least some carbon still left. But for those who may be doing a much more sophisticated BNR system, where maybe you're doing the denitrification in the middle somewhere of a multi-zone system, like Argenfo or something, where you've got, you know, zones in the middle where you're trying to do it, and you've probably gotten rid of a lot of the carbon by that point, you may want to do some dosing of that as well. So we actually have a whole series of chemical dosage objects that look like this one. They're up there with the influence and the influent panel. And they have different colors. The yellow one is the one that is COD chemical dosage. It's basically there to do carbon dosing and other kinds of dosing for BNR. What I recommend is, if you're going to do this, then I recommend you use the dual inlet plug flow tank object. That's the one that has two inlets here, plus a third one for the recycle that comes back in here from the clarifier. So it's our dual inlet one, because this top connection point is the one that's designed specifically to accept the flow of your methanol or what have you. So now, when you open up the menu of your carbon dosing object, you'll see that you have to first pick what kind of chemical you want. And so we have a lot of different options here. And so mixed substrate, by the way, is for things that are like micro C and that kind of synthetic carbon source that you might have. These ones, the upper ones there, we kind of know the numbers for. The mixed substrate, you can actually specify the strength and composition. It's sort of a customizable one if you like. I'm pretty sure the number that we have there is pretty good for micro C and that sort of thing as soon as you open the menu. Okay, so now let's do a very similar type of sensitivity analysis on carbon addition. Okay, so I am going to go to a different layout now. Okay, so here, I'll just point this out before we go. Here's our methanol dosage, and it's going into the top connection point of this MLE tank, and it's going into the very first zone, which is the one that is the anoxic zone, where we're doing our denitrification. Otherwise, all the rest of this is the same as the previous example I was just showing. Okay, so I'm going to leave everything else the same up here, except I've set by default the anoxic zone fraction to 40%. That's kind of like taking the information that we had from that previous example and saying 40 is like pretty much close to that sweet spot. Now let's take what we want with our carbon dosage, and we can play around with dosing and seeing what happens. So what I did was I actually set up that same kind of output graph, but this time I'm going to run a dynamic simulation for 20 days. And while it's running, we'll start adding some methanol. So I'm going to stop here for just 1 second and say here, these are the two things you need to look at the bottom. This is the total effluent nitrogen here. And I'm going to start adding just a little bit. And Okay, that didn't have a huge effect. It's dropped a little bit, so let's add a little bit more. And then we should be able to see a bit more of a decrease in our effluent total nitrogen. So what that meant was we were, at least to a certain degree, a little bit carbon limited in being able to do that amount of denitrification. This is the effluent nitrate up here, so you can see it actually has come down. Now, the downside is if you keep dosing a little bit too much, it's going to have diminishing returns down here if it's not really the, completely starved for it. And you're going to end up having, carbon come out in your effluent if you're not otherwise getting rid of it all. So you're going to probably grow more biomass and have a higher mixed liquor and so on. So that's what we're kind of seeing over here, is that our effluent VOD is actually creeping up a little bit the more dosage that we add here. So, so what we can do then is we can actually do a little bit of an experiment by running a sensitivity analysis on this as well. So I'm going to reset this, reset the model. I'm going to go up here and turn this one over to a step that, and turn on the analyzer. And then we will do basically exactly the same thing that I just showed you before, except it's going to step through and make a relationship for us of total effluent nitrogen versus the total effluent nitrogen versus the carbon dosage. So we can see here that, of course, it does drop with no carbon dosage. We're at 9.2, and with half a meter cube per day, we're at 6.9. So we can drop it like 2.5 milligrams per liter here. But of course, our BOD really takes off, all other things being held equal. So this is another analysis that you could do. You could, in fact, combine these types of analyses and iterate through them in order to sort of look at many of the other parameters that are part of the decision choices that you have to make when you're setting up and designing your MLE system. Okay. So just kind of winding up some of those thoughts about using just very simple one parameter sensitivity analysis on your denitrification process. So we did it here for anoxic zone fraction, and we did it for carbon addition, You could do it on that internal mixed liquor recycle value. And so that's a number that you could test and see how high you want to be able to go with that, or what is a good value to use there. You could do it on wastage so that you could see how it affects your mixed liquor and SRT, and of course all of the other effluent parameters, just like we were looking at. And you could also do it to determine good spot for low simultaneous nitrification and denitrification operation at a sort of a low DO. And in fact, that is actually the next thing that I want to demonstrate here as well. So all of the examples I was showing you before with the MLE process, it was sort of conventional plug flow tank, which had some anoxic zones and some aerated zones. So now, what I'm going to do is show you one completely mixed reactor that is going to alternate between aerobic conditions and anoxic conditions. And this actually came from a project that was sort of, it was an industrial application, actually. So the concentrations were much higher than you would see in the regular municipal plant, but the concept was the same. The demonstration I'll show you here shortly. But in these cases, what you do with one single tank is you turn on the air for a while, and then you turn it off and let it be anoxic for a while, and then back and forth. And it's the relative length of time that you do that becomes the sort of interesting, most important part of that. So when you have the air on, so let's put the bubbles in this tank. So we turn the air on. That is going to allow the biomass that is in there to do nitrification, so get rid of the ammonia and produce the nitrate. Then we turn the air off for a period of time, and then of course it's going to do denitrification. But at the same time, all of the new wastewater coming in, you're not removing any of that ammonia. So that will start to build up again. And then this alternating back and forth system allows you to sort of just sort of bounce back and forth between having ammonia and having nitrate. And doing that back and forth will allow you to sort of do it in the same tank. So you can actually have control systems that can optimize total nitrogen removal by adjusting the cycle times. And we're actually going to use our model right now to analyze that and find that there's a sweet spot of low, but not zero, dissolved oxygen. That is that sort of partially aerated spot where the nitrification and the denitrification can occur simultaneously. So if we go way back to the equations that I showed you at the beginning of the webinar, there are places where you can find a DO that kind of exists around the levels of those half saturation for oxygen values. So like 0.2, 0.3, something like that, where you're going to get some nitrification and some denitrification because neither one of them will be turned all the way off. So what that looks like in terms of process is, instead of saying I'm going to just completely get rid of all the ammonia, when I go to the anoxic phase, I actually don't go all the way off. I actually leave some aeration happening there. And you can kind of find a medium ground where you're not going to do as much nitrification and ammonia removal as you would otherwise, but you can sort of do it enough that it can get it into nitrate and then denitrify it all in one shot. So just a word though, of course, we're operating at low DO conditions can also have a whole bunch of other issues that are separate outside of this little discussion that we're having here at the moment, which is the potential to grow other kinds of biomass that could cause havoc throughout your plant. And also, of course, the fact that you may need other ways, other mixers and so on to keep the mixed liquor completely mixed, because otherwise if you're a system where you rely on the diffused air keeping everything mixed, then you're going to have some solid settlement if we don't do that. Okay, so how do we do this in the model? So there is a nice way to set this up using the timer controller. It's this particular object. It's in the process control panel on your drawing board on the left-hand side there. You put one of these on the drawing board, and then you open up the menu, turn it on, and then fill out the details of what you want to do. So in this particular case, this is the cryptic variable name for the aeration in this completely mixed reactor. And then we have a cycle time. So for an entire cycle time of 60 minutes, we want the air to be on for 30 of those 60 minutes. And then we want the airflow to be this much when it's on and this much when it is off. So it's kind of a square wave, just like it's showing in the panel there. Okay, so let's look at a couple of examples of that. Okay, so let me get out of this one, and we will move over to a different layout. So again, this is the one, I actually adapted this from our sample layouts menu, and there's an example under software features for the optimizer that uses this. I've kind of simplified it down a little bit, but basically this is the aeration controller here. And as I was showing before, we've specified that we want it to do control the aeration. So to have it on and off and so on. And it's going to control the air in this one completely mixed tank, which is going to go back and forth between being aerated and not aerated. Okay, so now I set up a different set of graphs here to hopefully be able to tell the story relatively straightforwardly. So right now, the parameters that I'm going to play around with are the cycle time and the on time within the one cycle. So right now, we're saying our cycle time is 1 hour, and this is the amount of time we're going to aerate within that hour. So as you can see right now, we're going to start out with 100% air on all the time, so fully aerated. So I'm going to run a dynamic simulation, and we can see that that is the case. So just let me pause that for one moment. You can see right now the ammonia is very low because we're fully nitrified. We've got lots of nitrate, that fully aerated zone. And our effluent total nitrogen is, of course, high because we're not doing any denitrification yet. I plotted the oxygen here on this graph on a scrolling time graph so that you could see it going up and down nicely and easily. Okay, so let's continue this along. And I'm actually going to knock this down to, say, 45 minutes. So now what we can see is, hopefully you're able to see that our nitrate came down a little bit and the ammonia went up just a little bit. What's happening here is the DO shows that when the air goes off, the DO goes down very quickly down to 0. And then it comes back on again and it pushes its way up and then it keeps going up until the next time at which it turns off again. And it just keeps going back and forth in that cycle. So we have some anoxic time and some aerated time. And we also have some time passing forth across that in-between part, partially aerated point. Okay, so we're going to keep doing that That's 15, sorry, that's 3/4 of the time. So 45 minutes on, 15 off. So now I'm going to switch it to 30. So it goes 30, 30. And we can see here now, of course, it's not, the DO is not getting up as high. I hope that comes across in GoToWebinar here. Maybe I should stop it so you can see it. So it doesn't go as high as it did before because it is now on for not as long as it was before the next time, and it turns off again. So it's only getting up to like not even 1 milligram per liter now because it's only got on for 30 minutes. So, but now look, we got lots of great denitrification happening here. Okay, so let's move it all the way down to 15 minutes. So let me continue that. So this is where we're at now, and I'm going to knock that down to 15 minutes. So it's now 15 aerated, 45 not aerated, so 45-minute anoxic zone. And of course, this is not doing very well because we can see here that this is ammonia, so we're really not nitrifying fully anymore. And now our effluent total nitrogen has come back up again. So really what this is telling us is if we have a fully aerated zone, we're going to have not very much ammonia and lots of nitrates. Our total nitrogen would be high somewhere. Oops, let me run that again. I was taking too long to tell my story here. Somewhere in the middle is the best spot. And then if I keep going, then it goes too far the other way. And so that's the optimization that we're going to look for right now. Okay, so the next step, what I'm going to do then is I am going to use the GPSX optimizer function to find out what is the best value of these two settings here. So not only are we going to say what is the on time, we're going to say how frequently do we want that cycle to turn over. Is an hour too long? Maybe it'd be better if we went 15 minutes on, 15 minutes off. You know, like make it happen every half hour. So I've got that set up in my last layout demonstration here. So this is exactly the same layout that I just showed you, except now I've got the optimizer already configured here. So the optimizer is a process that you have to go through and set up, specify what it is that you're trying to do. I set it up, this example, with total nitrogen as the target. So I can even actually see that right here. Target variable is total nitrogen, and I set it up that I wanted it to be as minimized, to make it as low as possible as part of our search routine. And I've also specified which parameters that I want to have adjusted, and those are the two ones that are up here. So it's going to start out from that fully aerated point, and I got to turn on the optimizer, and I'm going to let it do its thing. So like the analyzer, it is going to make changes to these values. So it's now searching around, trying to find the value that will get us the lowest point on this effluent total nitrogen graph as possible. So it's the value here on the right-hand side after 1 day. It's trying to get that as low as it possibly can, and it's continuing to making changes here. It is kind of hit that 50% point, kind of like what we found by just playing around, but now it's making the whole cycle smaller. Okay, that one is a worse guess. So it went back to making it a little bigger. And then eventually it converges. So this is the best I can do. So basically 9.6. So it's like saying roughly 10 minutes on out of a total of 20 minutes. So 10 minutes on, 10 minutes off. That's the answer that it gave us as being the best, most optimal settings for our alternating aeration system. So so now that tells us we can get down to, what is this here? That's about a little under 5 milligrams per liter of total nitrogen. Okay, so I realize I've taken slightly longer than normal to tell my story here, so I'm going to pick it up. And I just wanted to say that that optimizer tool is really, really handy for doing really interesting analysis with your model. So I recommend doing a sensitivity analysis first to sort of see what the effects are changing things. Like do it on one variable at a time just to get a handle for it. But then with the optimizer, you can combine several variables at once. Sometimes you may need to iterate through different optimizations, like optimize carbon dosage first and then do something else and then come back with that new answer and then optimize the carbon dosage again. Maybe you can combine them all in together. But the choice of the target variables and the constraints is very important. The constraints meaning I don't ever want to go below a certain airflow because maybe that would mess up my mixing. And you need to sort of confine it to realistic performance targets. Like the optimizer itself is only going to do what you tell it to do. Remember, one of the most enlightening things I ever did when I first joined Hydromantis way back in the day was I thought, okay, this is great. I'm going to just use this tool all the time. And first thing I did was I said, minimize energy at this wastewater treatment plant. And of course, what did it do? Well, it shut off all the pumps and it shut off the blowers and everything. Yeah, well, it optimized the energy, made it as low as possible, but also turned off the treatment too. So you need to make sure you've configured your optimization question in the right way. But doing total nitrogen removal is great, actually, because it is basically, if you go too far one way, it's going to bring it back, or too far the other way, it's going to bring it back. So it's a nice example of a way to use your model. Okay, final thoughts as I sort of wind up the slides here. Mantis 2 model is, described in quite a lot of detail the nitrification and denitrification processes. For those of you who are into using our Mantis 3 model, that's the Mantis 2 model plus the GHG, greenhouse gas, and carbon footprint analysis. That model is actually even more detailed on the denitrification side, a 4-step denitrification process where we want to capture the nitrous oxide and other things there. The kinetic parameters menu, has those constants and parameters that you can adjust to calibrate your nitrification and denitrification process. The analyzer feature can be used to study those relationships in a really, really fast way, and I find it really helpful and enlightening. And then the optimizer function is the one where you can say, okay, here's 2 or 3 parameters that I want you to find me the best combination of to achieve a specific target. So there you go.